Welcome to Chapter 9, Molecular Geometry. We saw in Chapter 8 that Lewis dot structures helped us understand the composition of molecules and their covalent bonds. However, Lewis dot structures do not show one of the most important aspects of molecules, their overall shapes. And in science, it's lots of times said that form leads to function. And if we know the form, we can understand the function of the molecules. Molecules have shapes and sizes that are defined by the angles and the distances between the nuclei of their component atoms. Chemists often refer to molecular architecture in describing the distinctive shapes and sizes of molecules. The shape and size of a molecule of a particular substance, together with the strength and polarity of its bonds, along with the shape and polarity of its bonds, largely determine the properties of that substance. Some of the most dramatic examples of the important roles of molecular shape and size are seen in biochemical reactions and in substances produced by living species. For example, in the opening photograph of this chapter, Chapter 9 right here, it shows a tree that was found right near the Pacific Ocean called the yew tree. Well, in 1967, a couple of chemists isolated from the bark of this tree a small amount of a molecule that was found to be one of the most effective treatments for breast and ovarian cancer. This molecule, now known as the pharmaceutical Taxol, has a complex molecular architecture that leads to its powerful therapeutic effectiveness. Even a small modification to the shape and size of the molecule decreases its effectiveness and can lead to the formation of substances that are toxic to humans. Well, recently, chemists have discovered how to synthesize the drug in the laboratory, which made it more available and has saved the yew tree from extinction. It took 6 trees to be harvested in order to provide one treatment of the Taxol. Now, there's a lot of other things that depend on the shape and the size and the formation of the different molecule, and we're going to look at these molecular shapes here in Chapter 9.1. So it's helpful to have your book out because you can look at some of these colorful pictures. I'm going to put them on the screen too and talk about them as we go. But it's helpful to have that out alongside of you as well. And then you'll need your notes as well. These notes right here, Chapter 9, Molecular Geometry Theories. Shapes, forms, leads to function. And we're going to fill in this shapes chart that's on here, and we're going to talk about where those shapes come from. You might want a separate piece of paper out too, so then you can jot some extra notes down as well. So pause the video now to make sure that you've got those things in front of you before you move ahead. We saw in Chapter 8 we used Lewis dot structures to account for the formation of covalent compounds. Remember, covalent compounds are made of all nonmetals. And so it's these nonmetals that are stuck together that end up having covalent bonds where there's a sharing of electrons. And then when this happens, this sharing of electrons, for example in CCl4, we get these things called covalent bonds. We illustrate those covalent bonds by these dashes. And we illustrate these electrons that are not involved in a covalent bond as these things called unshared pairs. So we give fancy names to both of these things. We called these bonds shared pairs of electrons. And then we call these things right here that aren't shared with something, we give them a real fancy name. We call them unshared pairs. I'm being a little facetious there, but unshared versus shared pairs is something, if I just say those words, maybe not as obvious as if I point them out and say, hey, look, these are shared between these two. And then these guys right here, these are not shared. And they make a difference in what happens in the shape of a molecule. So the thing that governs the shape of a molecule is a real fancy named theory called the valence shell electron pair repulsion theory, which is symbolized by the acronym VSEPR, which looks kind of daunting at first glance, but it stands for valence shell electron pair repulsion theory. And the theory itself is really simple, but the name is really complex. Valence shell remember, electrons that are in the outermost shell of an atom. Electrons, of course, are the negatively charged things out there. And then pair means 2 electrons that are either shared or unshared. And then repulsion means pushed away. pushed away. And all the valence shell electron pair repulsion theory says is that if there are two electrons, shared or unshared, near each other, they push each other away. And they push each other away as far away as they possibly can. And when they do this, they make the molecule into various shape. And depending on the number of shared or unshared pairs of electrons that are around a central atom, it will create a particular shape. As a matter of fact, we can see here in this picture that's in your textbook, if we have a central atom and we have two shared pairs of electrons and no unshared pairs around here, we'll get one of the atoms on this side, one of the atoms on this side with a 180-degree split between the two. This is known as a linear shape because it makes a line. If you see here, if we have three atoms bonded around a central atom, they'll move as far away from each other as possible, and you end up with a shape that's known as Trigonal Planar because it's all in one plane if I turned it sideways. And then, of course, there's far away as possible, which is 120 degrees, you know, if you split a circle up into three portions. This one's a little bit more complex. This is four things bonded around one central atom. And you have to remember for this one that this is three-dimensional. Now, if it was just four things bonded around a central atom, you'd say, okay, I can do 1, 2, 3, 4, and this is a 90-degree angle right here, and that's as far away as they can. But we don't live in a two-dimensional world. We happen to live in a three-dimensional world, lucky us. And so when you three-dimensionally take things and put them as far away from each other as possible, it turns out to be 109.5 degrees. And if you connect the edges of these, it actually forms the shape of what's called a tetrahedron. And so it's called a tetrahedral shape. Now, if we bond five things around, we get a shape that's called Trigonal Bi-Pyramidal, which is 90 degrees and 120. And then lastly, if you bond six things around it, you get the prefix oct, because if you connect the edges right here all around it, you get an 8-sided figure, which is known as an octahedron. And notice the bond angles there are all 90 degrees. In addition, if we have unshared pairs of electrons, unshared pairs of electrons actually have more force of repulsion than shared pairs. We can get these electrons, for instance, take the tetrahedron and say we had an unshared pair of electrons right here. These cause the pushing of these bond angles to become closer, and it forms a shape that's called Trigonal Pyramidal. And if we have two unshared pairs of electrons, as in this, it forces the shape to be what's called bent. Now, these names and words might sound a little bit daunting at first, and you're like, oh my gosh, I got to learn those shape names and things, but I'm going to give you some help. I'm going to give you some help to help remember these shapes and identify what they are. And we're going to fill them out on a table. And I'll give you a good way to recognize and figure out what kind of shape different molecules will make based on how many shared pairs, in other words, bonded pairs of electrons there are, and how many non-bonded pairs or, unshared pairs of electrons there are. So here's the shapes chart. We're going to take a look at the shapes chart, and we're going to figure out what shapes different things have based on the number of total electron domains something has, the number of bonded domains of electrons, non-bonded domains. Then we'll know the bond angle, the name of the shape, and then I'll give you a way to remember it all as well. So first, what does this fancy word domain mean? Domain means an area where electrons exist. Where electrons exist, whether they're bonded to something else or whether they're not bonded. Whether they're bonded or whether they're not bonded to something else, okay? If they're bonded to something else, then we call them a shared pair of electrons. If they're not bonded to something else, we call them an unshared pair of electrons. Both are an electron domain. And we actually call it the electron domain geometry because it's where the domains of electrons exist around the center of an atom. You can see on this page in your textbook, they try to do a really nice job of showing it in 3 dimensions, that we've got 2 electron domains illustrated by these purple little bubbles, 3 electron domains, 4 electron domains, 5, and 6 electron domains, and that's the most we'll see is 6. And you can see that each one of these is given a particular electron domain geometry: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral, and each has predicted bond angles for that number of electron domains that are around the central atom. Now, depending on whether the electron domains are shared or unshared, it determines the actual bond angles that actually exist. And we're going to go through each one of those individually, and I'll give an example as we go along. So the first one, make sure you have this page in front of you because we're going to fill it out now, is when there's 2 electron domains, 2 are bonded, 0 are non-bonded, and it has a bond angle of 180 degrees, and this is called linear. And an example of this would be if we had carbon dioxide. Carbon dioxide has a shape of C double bond O, double bond O. Let's make sure I'm zoomed in enough so you can see that. Okay. And you'll notice that about this central atom right here, there's a domain of shared electrons right here. I know it's a double bond, but it's still just one domain where electron bonding takes place. And then right here is another domain of electrons where bonding takes place. And so the angle between these two is 180 degrees. And so we get the shape called linear. And the remember all is the word love. L for linear, L for love, and it's actually going to spell a little remember all thing for you, so write down the word love. Okay, because you love electron domains so much, maybe? Well, we'll see. Electron domains, 3 bonded, 0 non-bonded. So now when we do that, we spread things out, and it turns out to be a 120 degree bond angle, and it has the name that's called Trigonal Planar. And there's a nice picture of this in your textbook right here, where you can see here is the central atom, bonded domain, bonded domain, bonded domain right here. It's called trigonal planar, and their example right here is BF3. Boron only has 6 electrons around it, which is one of those exceptions to the octet rule, and so this bond angle ends up being 120 degrees, and the name is trigonal planar, and you need to memorize that name, trigonal planar. And the remember all for this is the word 2. Love 2. Okay, T for trigonal. Okay, trigonal. Because it kind of makes a triangle shape if you look at it. Trigonal, see, trigonal, trigon. Okay. Next, 3 total electron domains. 2 bonded, 1 non-bonded. 2 bonded, 1 non-bonded. And then what happens to the shape? Well, since we have an unshared pair of electrons here, it actually squishes the bond angle to be a little bit less than 120 degrees, and your book does a nice job with this picture as well. You can see here, this purple part right here illustrates an unshared pair of electrons, and since these are a little bit more dominant and take up a little more space than a shared pair of electrons, they actually force the connected atoms a little bit closer together, and this bond angle is a little bit less than 120 degrees. Let's just say it's about 117. You just need to know that it's a little bit less, and it has a shape named bent. And the example here they give is the NO2 -1 molecule, or the nitrite molecule. I'm sorry, nitrite polyatomic ion. And the name of the shape, once again, if you're filling in your chart, is bent. And this has a remember all of love to B. Okay, LTB, love to B. Okay, love for linear, T for trigonal, B for bent. Okay, thirdly, 4 and 4. 4 bonded domains, 0 non-bonded domains, 109.5 degrees, and yes, you do have to know the angle. It's called tetrahedral, and then love to be, and now it's the word the for the remember all, the T for tetrahedral, and here's an example right here, CH4. They do a nice job in your book of doing a three-dimensional structure here and showing you that one of the bonded domains comes out at you. This one goes back into the book, this one back into the book, and this one straight up. And the way that chemists illustrate this is with a structure that looks like this. You can see these dashes right here illustrate that it's in the same plane as the paper. This wedge shape right here means it's coming out at you. And then this little dashy, dashy, dashy thing right here means that it's going back into the paper away from you. So that's called the dash line wedge, if it'll ever focus in on that. Wow, that's terrible. There we go. Representation showing three-dimensionally that the wedge one comes out at you, goes back away from you, and here these are in the same plane of existence. So that's four bonded, 0 non-bonded, tetrahedral, love to be the. Okay, next is 4 total electron domains again, 3 bonded, 1 non-bonded. 3 bonded, 1 non-bonded. And so in this one, now the non-bonded pair of electrons actually forces the bond angles a little bit closer, and it turns out to be about 107-degree bond angle. And this one has a fancy name. It's called Trigonal Pyramidal or Pyramidal. And the bond angle, or the remember all, is love to be the play, P-L-A-Y, P for pyramidal or pyramidal. Okay, and you can see this in the picture here. Here's the trigonal pyramidal. Notice we've got this unshared bubble of electrons right here, which is a little more powerful than the shared pair. Forces these electrons closer together, forcing this bond angle to be 107 degrees. And yes, you need to memorize 107, and you need to memorize a trigonal pyramidal. You need to become very familiar with this. The example of this is the ammonia molecule, NH3. You can see here's an unshared pair of electrons, and then they use the nice dash line wedge illustration here to show you that one of the hydrogen is coming out at you. Once again, no focus. Let's see if we can get this to focus a little better. There we go. One's coming out at you, and then one's going back, and one of the hydrogens is in the same plane. Next, 4 bonded, 2 non, 4 electron domains, 2 bonded, 2 non-bonded. Here's 2 non-bonded, forcing this bond angle right here to be approximately 104.5 degrees. May sound insignificant. It's only a couple degrees different from 107, only a couple degrees different from the 109 right here, 109.5. But it makes a huge difference in their physical properties. As a matter of fact, we'll see that in our intermolecular forces unit, chapter 11, that this structure, bent, is critical in water's function. You can see right here, good example is water. Whoa, there we go. You can see water has a hydrogen going back into the paper, one coming out of the paper, and then we've got those 2 unshared pairs of electrons that force it together to have a 104.5 degree bond angle. So this one, 2 and 2, 104.5 degrees. This one is called bent. I know there was a bent up above here, but this is the second bent. And so this is the remember I'll love to be the playboy. B-O-Y. Okay, L-T-B-T-P-B-B for bent boy. Okay, and the first letter of each one goes with, you know, a letter name of the shape. So remember love to be the playboy, and now you all of a sudden have 6 of them memorized. All right, next. We get to the more fun ones when we have 5 bonded domains, 5 shared, 0 unshared, 5 shared, 0 unshared. These get to be a little bit more exciting because they have some bigger names. This is called, this has 2 bond angles, by the way. It has bond angles of 120 degrees and also 90 degrees. And this one is called Trigonal Bi-Pyramidal. Love to be the playboy. And now this one starts kind of a new sequence. I'm just going to put a line here. This is the word test, T-E-S-T. Okay, and well, T stands for trigonal, T for test. Okay, and we'll come back to that in a second. You can forget the EST part, but just remember it's T because it's from the word test. Trigonal Bi-Pyramidal. And your book has a really nice picture of this right here, of a trigonal pyramidal electron domain geometry. And you'll notice, if I can get this to focus, please. Yeah, there we go. Whoops, go ahead. There we go. You'll notice that there are two planes of existence here. There's this plane that goes into the paper where these three electron domain geometries right here have the 120 degree bond angle. That's called the equatorial domain, because it's kind of like an equator. Equatorial domain goes around the center. And then there's this bond that goes up and down, and these form a 90 degree bond angle with them. And this is known as the axial domains. And as we go along, we'll find out that when we remove bonds from here and put unshared pairs in there, they come from the equatorial domain first before they ever go from the axial domain. That's where we'll remove them from. And this is called Trigonal Bi-Pyramidal. Whoops, there we go, Trigonal Bi-Pyramidal. And like I said, right here is the 120 degree bond angle, and then right here is the 90 degree bond angle. So 90 versus 120, and an example is PCl5. Notice it's one that has an expanded octet, and therefore can have 5 bond domains around it. Okay, next one is 4 and 1, and I'll zoom in on it right away. This one has 4 bonded domains and 1 non-bonded domain. It's called Seesaw. And you can see that from the equatorial domain right here, we lose 1 bonded pair. And then this bond angle right here actually becomes reduced. And so it's no longer 120, maybe like 117 degrees or so. This bond angle remains at 90 degrees. And when we do that, if we tip it on its side, these would be the bases of the teeter-totter, or the seesaw. An example of this is SF4, and you'll have to come to class sometime to see me actually make the seesaw shape. SF4. Next one, if we lose two domains of electrons, you can see we've got 2 non-bonded domains here, and then 3 bonded domains right here. These still are 90 degree bond angles right here, so the only one to know for 3 bonded, 2 non-bonded is 90 degree bond angle. An example is ClF3, and this is known as T-shaped. T-shaped. And then the last one, if we remove the last shared pair of electrons right here, remove the last shared pair of electrons, so then we have 2 bonded and 3 non-bonded pairs of electrons right here. This would turn out to be what's known as a linear shape, because it's a line 180 degree bond angle right there. And these in the equatorial domain, of course, would be all gone. And then we just have the linear molecule right here. And that's the actual name, and XF2 is an example of that. So let's fill in our chart back here. I'll zoom back out. We'll finish filling in the chart for the 5 electron domain geometry, guys. So 5 and 4 bonded, 1 non-bonded. It's called Seesaw. Seesaw, and Seesaw is TS. Okay, TS. Then 3 bonded and 2 non-bonded. That has electron domain geometry of 90 degrees, and it's called T-shaped. T-shaped is another T, so TST for test. It's missing the E, so that's why I told you to kind of cross this off up here. TST, okay? And then 2 bonded, 3 non-bonded gives you a 180 degree bond angle, which has a shape called linear. And I know we used the word linear up above too, but it is another linear shape because it has a 180 degree bond angle. So that's the letter L. So TST, that's going to be test. TST, spelled strangely, TST. And then we're going to fill this bottom in right here. L is the first letter of one more word. So we're on to the last ones here. 6 bonded, 0 non-bonded, 5 bonded, 1 non-bonded, 4 bonded, 2 non-bonded. The 6 and 0 ends up having 90-degree bond angles. It's called octahedral. And so it has an O right here for the remember all, LO. 5 bonded, 1 non-bonded ends up with a name called square pyramidal. So the letter S for square, LOS. And then the last one, a 4 bonded, 2 non-bonded, and 90-degree bond angles ends up being square all in one plane, so we call it planar. Square planar, which is another S. So the remember all for the 5 and 6 electron domain geometries is test loss, TSTLOSS. So if you remember love to be the playboy, test loss, and remember there's no E in test, now you remember the first letter of every one of the shapes and you can regurgitate them and then use them on a test someday in your life, or a quiz maybe that's coming very soon to you. Let's take a look at some of those shapes. Here's the 6 bonded, 0 non-bonded, octahedral electron domain geometry. 6 bonded, 0 non-bonded. Let's see if we can focus in on that a little bit better. Not so. Maybe I can try it like this. Bring this just a little bit closer. Okay, here's octahedral. You can see we've got 90-degree bond angles here between everything. We have an equatorial domain once again right here. And we have an axial domain once again. They're all 90 degrees. Remove one. It's removed this time from the axial domain. Okay, axial domain is removed first from the octahedral. And notice then this bond angle right here no longer is 90 degrees between these. It's a little bit reduced. So a little bit less than 90. And then if we remove them from the top and the bottom, notice these guys in the equatorial domain all remain. And they all remain with 90-degree bond angles right there, and they're all in one plane, so that's why they call it square planar. Example of this, XF4, example of this, BRF5, example of this, SF6. So, back in summary once again of our shapes, here's the entire chart. You need to know the number of electron domains, bonded and non-bonded, the bond angles for each one, the name of the shape, and of course the way to remember the shape is love to be the playboy, test loss. In our next video cast we'll take a look at some consequences of these shapes, and once you can identify what the shape of a molecule is, now you can know a bunch more about the molecule and something called its polarity. Once you can identify its polarity, then we can go on and take a little closer look at what the bonds actually do. So make sure you've got this completely filled out. Memorize your angles, memorize your names, and you're good to go.